Hey, hey, come on, grab your seat. I've got your coffee. All right. So, how's the homework going? Have you survived Big O? Did you survive linked lists, trees, graphs, all that fun stuff? All right. So today we've, we're gonna get our we've run into a problem. Um, Actually, it's the same problem every real application runs into. We've got data. We've just got nowhere to put it. So our our little cafe application. So we've got inventory, coffee, tea, milk, sugar. We have also got things like orders and customers, um, and last time we spoke about different ways that we could organize this information in memory: arrays, lists, maps, trees, all sorts of fun structures. And that's all great until the application turns off. What happens to all of the data then? It's gone. I close the application, and tomorrow morning, Java starts with a blank slate. So it's not exactly going to work, and I don't want to count my coffee inventory every morning. I mean, we need persistence. Come on. We need somewhere that our data can live after the application shuts down. And that's where databases come into this. So, at its simplest, a database is a system for storing and retrieving information, and there are lots of different kinds of databases out there. But today, I want to talk to you about a relational database. And for our little cafe, we're going to be using something called SQLite. So, this is nice because the database can live right alongside our application as a file. No database server, no configuration, no giant infrastructure, just here's our database. And now we can start designing it. So we can start out with our inventory. Um, we could create a table and call it products. And now, if you're completely new to SQL, then don't let this scare you. We're basically just shaping our data. We're saying that I want a table called products, and I want to have every product to have an ID, a name, a quantity, and a price. The table is our structure, and now each row represents one product. So our database might look something like this, and suddenly our cafe has a memory. So there's something else important that we don't just want to store our data, we also want to make sure that our data makes sense. So if we look at name text not null basically means that this is a required value. We don't want a product that doesn't have a name. And then something like quantity, integer, not null, default 0, well, that's saying that the quantity is an integer, it's required, and by default, we're going to set this to 0 unless otherwise specified. So these are constraints. And constraints are incredibly important because your application isn't the only thing that can make mistakes. If the database itself can enforce the rules, that's a whole other layer of protection. So now every product needs an identity. That's what our ID is. And it's our primary key. Primary key, well, this is a unique identifier in a row. So product one, product two, product three, product four. These IDs give us something stable to reference. And these are there are different ways that we can generate these IDs We might use an auto increment. We might use a natural key. Sorry, we may use things like a product code that already has meaning, or maybe we could use something like a UUID, and each approach does have its trade-offs. For our little SQLite application, um, an integer primary key is perfectly reasonable. So now imagine we have employees and orders and customers. Now, how do these tables know about each other? This is where relationships come in. And imagine an order, and an order belongs to a customer. Okay, so we have a customer. Customer one is Mike, two is Sarah, three is Andrew, and then we simply have an order of 101 belongs to customer one, 102 to two, 103 also belongs to one. Now, that customer ID inside of the order is what's known as a foreign key. It is a primary key somewhere else that is being used internally as a unique identifier for what belongs with it. It is telling the database this order belongs to that customer. Now the database can enforce referral integrity. So if an order says it belongs to customer 42, but customer 42 doesn't exist, then that's a problem. And the database can stop us from creating that broken relationship. That is one of the beautiful things about a relational database. So they don't just store information, they can also enforce relationships between informations. And there are a few types of relationships that you're going to see constantly. There's a one-to-one, where one employee might have one employee profile. There is one-to-many, where one customer may have many orders. That's probably the relationship you'll see everywhere. And then there is a many-to-many. So imagine products and suppliers. So one supplier can provide multiple products, and one product could potentially come from multiple suppliers. Now, you can't just stick one supplier ID onto the product and call it done. Instead, we introduce another table, something like this, where product ID of 1 belongs to supplier 10, product 1 to supplier 11, product 2 to supplier 10, and the little table is called a junction table or a join table. And now we've represented a many-to-many relationship. So what happens if I delete a customer? What happens if I delete their orders? We need some rules. And maybe the database should delete the related records too. That would be on delete cascade. Now, maybe we want to keep the related record but remove the association. So that where we do on delete set null. And this can make sense. These decisions are part of the database design, and they matter because deleting a row isn't as simple as just delete it. Your data may belong or be connected to other tables. You don't know. So now you've got your database and you've actually got it, you've now need to talk to it. This is where SQL, or structured query language, comes in. And SQL is a declarative language. And that is an important distinction. With Java, you tend to tell the compiler how to perform a task. With SQL, you genuinely tell the database what data you want. For example, select all from products. This basically, give me everything in the products. Now we can filter it, select all from products, where quantity is less than 10, and we're basically saying, give me all the products that we're running low on. And we can then sort it, give me select all from products ordered by price descending. And this gives me a list of products from most expensive to least expensive. Maybe we can limit this. Select all products, limit 10. And we can also give it an offset if we want to start maybe with product 5 and get the next 10. this is the foundations of pagination. Now, what if I don't want individual products? What if I want information about the products? What if the product, how many products do we have? What is our average price? What is the most expensive thing? What is the total quantity of our inventory? These are where aggregate functions come in. Things like count, sum, average, min, max. For example, select the count of everything from products. And this basically says, how many products do we have? We can then group this information together as well. So imagine we have an inventory with categorized types, coffee, tea, pastries. So we could use something like group by and aggregate those categories. Um, and then having lets us filter the grouped results, and this is where SQL starts to become incredibly powerful because we're not just retrieving rows anymore. We're asking questions about our data and getting answers. So now we're going to do something that initially looks a little weird, but let's say I want to know which customer placed this order. The customer is in one table and the order is in another table. So we join them. Select customers.name, orders.name.id from customers, inner join these orders on the customer ID is equal to the orders.customer ID. And okay, read that almost like this, okay? Give me the customer's name and the order ID where the customer is connected to that order. And that's an inner join. But there are also different kinds of join. A left join lets us keep everything from the left table even if there isn't any matching rows on the right. There's also a right join, a full outer join, and even a cross join. So a cross join, okay, that a cross join produces a um, Cartesian product. So meaning every row from one side gets paired with that of the other. So usually that's not what you want. But understanding what it does is important. And the point isn't to memorize a list of joins. The point is to understand that our relational data is split across tables, and that SQL gives us ways to bring those pieces back together the way we want them. Now, I'm going to show you something a little more advanced. Suppose I want to number products within each category. I would do something like this. And that's a window function. And partition by lets us perform calculations across groups of rows without collapsing those rows into a single result like group by does. And you don't need to master this today. I just want you to know that SQL can do some remarkably sophisticated data processing. And that's why knowing SQL is so incredibly valuable. Um, Even when you're working with a framework that tries to abstract all of that away from you. But we'll get into Spring Boot later. Now, let's talk about something that might save us a little bit of save us from creating a terrible database. Imagine I store this, okay? Order ID, customer name, customer email, product name, and product price. Looks fine at first, but what happens when the same customer places 20 orders? then I'm storing their name and email 20 different times, and that's when their email, what if their email changes? It's no longer going to sync up. Now we've got 20 different records that we need to update, and that is data integrity. It's a problem. So normalization is about organizing relational data so that we reduce the unnecessary duplication and dependency problems. So you'll hear terms like first normal field, second normal form, third normal form, and eventually you'll get into a voice cod normal form. And I'm not going to make you memorize a bunch of textbook definitions. That's not what this is about. The important thing is to search for the piece of information at the place where it logically belongs. Customers belong in a customer table. Products, a product table. Orders, an order table. And relationships connect them together. So we're trying to avoid turning our database into a giant spreadsheet where everything just gets duplicated everywhere. Um, so there's another problem. Our database works beautifully with 10 products, but then once we start to get to that 10 million range, we run into, you know, select all from products where name is Ethiopian, and suddenly our database has a lot of rows to look through. So we can create this thing called an index. And think about the index at the back of a book. If you want to find something, you don't read the entire book. No, you flip to the last, look at the index, and go from there. Databases use data structures such as B trees to build indexes that can make lookups dramatically more efficient. Um, so we could create an index on products.name, or perhaps a composite index involving multiple columns, and something we can design. Um, Sometimes we can design a covering index so the database can satisfy a query directly from the index without needing to fetch the actual full table row. But indexes aren't exactly free. Nothing is free. They all take space. So every time we insert or update data, the index also needs to be maintained. So you can you don't just throw an index on every column and call it a day. Uh, you instead design indices around queries that your application actually performs. So now here's something I want you to get a little bit comfortable with. Don't guess, measure. If your query is slow, we can ask the database how it plans to execute this code. So with SQLite, we can use explain query plan, and in other relational databases provide similar things with things like explain analyze. Um, and these tools let us investigate what is actually happening in the database. Is the database scanning the entire table? Is it using an index? Is the query doing something unexpectedly expensive? Because just writing select whatever is easy, but writing SQL that performs well against millions of rows and large amounts of data, that is a different skill. Now, let's imagine something happens at our cafe. Okay, a customer buys 3 bags of coffee. We need to create an order, add the ordered items. We need to reduce the inventory. And what happens if, you know, step 1 succeeds, 2 succeeds, and then 3 fails? We fail to update. Now we've got an order saying that the customer bought coffee, but our inventory still says that we have it, and our database is inconsistent. This is where transactionals come into play, and a transaction lets us treat a group of database operations as one logical unit. So everything either succeeds or we roll everything back. And that brings us to something else that you're going to hear a lot in the database development: ACID. So atomically, the transaction happens as a unit. Everything succeeds or else it fails. Consistency. The database moves from one valid state to another valid state. Isolation. Con- concurrent transactions shouldn't interfere with each other in ways that produce invalid results. And then there's durability. Once a transaction has successfully committed, the database should persist the results. And these four properties are the fundamentals of reliable transaction systems. And by isolation, I'm sorry, but isolation gets particularly interesting because multiple things can happen at the same time. So imagine two people are trying to work with the same inventory. One transaction is changing our coffee quantity while another transaction is reading it. And while what exactly should the second transaction be allowed to do and see, that's where transaction isolation levels start to come in. So you'll encounter levels such as read uncommitted, read committed, uh, replicated read, and serialized. And these levels determine how much one transaction is isolated from another. Without getting too deep into the weeds, um, they exist to deal with problems such as dirty reads and seeing data that another transaction hasn't committed yet. Non-replicated reads are readings that the same row. Sorry, it's when you're reading the same row twice and getting different results because another transaction changed it. And phantom reads, these are where a query returns a different set of rows because another transaction inserted or removed matching records. And this is where database programming starts to become less about can I store this and more about can I keep this data correct when hundreds of thousands of things are happening at once. Now, what have we accomplished? We started with a simple problem. Our Java application has some data, and when the application shuts off, that data disappeared. So we introduced relational databases. We we designated tables, we added constraints, we gave our records primary keys, connected our tables with foreign keys, modeled relationships. We learned how SQL can retrieve, filter, group, sort, and even join our data. We've talked about normalization so that our data doesn't become a giant pile of duplicated information. And we talked about indexes so that our queries don't fall over when Cafe gets busy. So we also talk about the ACID principles. But there's something that we haven't done yet. We've got our Java application, we've got our SQLite database, and right now they're sitting on opposite ends of the table staring at each other. Our Java code needs to talk to that database, and we need to send SQL. We need to retrieve rows. We need to return those rows back into Java objects. We need to insert new records, update existing ones, and even delete things when appropriate. Now we're writing database access code. And this is where we're going to start um, connecting everything that we've learned from Java to objects, data structures, SQL, databases, and eventually we're going to talk about a framework that can help us bring all of this together, Spring Boot. But before I let a framework hide all the, mechanics and do magic, um, I want you to understand what's actually happening underneath. So, because if you understand the database, then when Spring Boot comes along and says, don't worry about it, I'll generate that query for you, you'll actually understand what's going on, what it's doing, and that'll put you in a much better place. So finish your coffee up, and next time we're gonna we're going to make Java talk to our database. And that's when our little cafe application starts becoming a real application. So keep your curiosity open, your skills sharp, and that coffee cup full. And I'll catch you in our next meetup.